In this video, we're going to explore something called the binomial theorem. Now, the content specifically of this video won't show you anything new as such, but we'll explore some old topics with expanding binomials in an attempt to draw forth basically the new content. Okay, so the first thing we'll do is let's check out how to expand this. Many of you will be able to do this in your head, I hope. But for those of you who can't, that's fine. So in order to expand a binomial like this, remember you do not, under any circumstances, quote, distribute that square. There is no such thing. What you do is rewrite the binomial. Again, squaring is multiplying something by itself. And the usual process for this is called FOIL. All right, our first times our first, outer times outer, inner times inner, last times last. It's a mnemonic device to remember how to distribute a binomial onto another binomial. But at this point, you get your x squared from your firsts, your 2x from your outers, another 2x from your inners, and last times last gives you that 4. So, of course, you get x squared plus 4x plus 4. Now, again, you hopefully you will essentially be able to do this automatically. All right? But the reason I wanted to bring this one into the mix here is mostly to notice what's going on with your x's. So the first term is x squared. The second term is x to the first. And the third term is essentially, it's not there, but there's an implied x to the 0 here. So what I just want you to notice is the descending nature of the variables in the successive terms as we expand this binomial. Keep that in mind as we expand example 1b. So this is a little bit different in that it's just a couple of variables, and this will help us, again, explore what is exactly going on when we expand this binomial, in this case, to the third power. So again, we're going to think about this as x plus y times x plus y times x plus y. And just as you were to do, if you were to do 2 times 3 times 4, you would do 2 of them. And then you get the whole thing, 24. So what we're going to do is we're going to multiply the first together and then multiply that product times x plus y. So let's do x plus y times x plus y times x plus y. So we're going to do just these two first. X times x is, of course, x squared. X times y is xy. Y times x is, of course, yx. And y times y is y squared. We still have this big mess times x plus y. Now, xy and yx are the same. Multiplication is commutative. So we can combine those two like terms to get x squared plus 2xy plus y squared. Those combine to make that. And we've got our x plus y. Now, we need to keep track if we're going to multiply this trinomial times this binomial. So I'll stay red for my first term. What you want to do is you want to distribute your first term into this binomial. So I'll take x squared times x, and then x squared times y. So I get x to the third plus x squared y. Now I will take 2xy and distribute it onto x, and 2xy and distribute it onto y. So I've got 2x times x is 2x squared y, plus 2xy times y would be 2xy squared. And then finally, we've got our y squared. We're going to distribute that onto our x and to our y. So it's essentially an extended FOIL, the acronym to remember that. Binomial times a binomial. So we got y squared times x. We've got a y squared x, which is the same as this, by the way, xy squared. And then y to the third. Now, combine all of our like terms to get our final answer. We get x cubed plus, these two are like terms, x squared y, 3x squared y plus 3x squared, and we get y cubed. So this is the expanded version of this binomial to the third power. Okay, so that's what we mean when we say expand a binomial. So what we've got here, notice, just like in the previous one, as we go this way, the x value descends, the exponent descends. X to the third, x squared, x to the first, x to the 0th. And at the same time, the y exponent is increasing. Y to the 0th, y to the first, y to the second, y to the third. And that's a nice pattern that you get. But what you also want to notice is at each term, the exponents actually add to 3. So you get 3, 2 plus 1 is 3, 1 plus 2 is 3, and then y to the third there. Okay? So basically, this would be the process if you wanted to do this, a binomial to any power. But I'll tell you what, if you got to x plus y to the 4th power, I do not want to do that. I do not want to do that by hand. So what's happened is, just like many other things, some wonderful mathematical minds have gotten together and written a formula, and we actually figured out part of the formula here. It has everything to do with this. Basically, you have some coefficients. You're going to have this little pattern going on in the exponents, and you'll be able to do this in a very formula-based way. So, next slide, we'll have the formula. Take a moment, jot it down. Then, once you get it jotted down, there's a lot going on. So, you have this binomial to the n power, and basically here is the expansion. This little ellipsis here allows for as many terms as possible, so it's very sequential. But basically, the one big thing that you really need to keep track of is what in the world does this mean? This is an alternate notation for a combination. It's an alternate notation for a combination. This n over 0 thing stands for NC0, so it's a combination. We'll get into combinations as counting methods a little later in 9.6, and then for used in probability in 9.7. But this is, in your calculator, you'll just evaluate a combination. NC0, NC1, NC2, until you get up to NCn. And what you'll notice is your first term is going to start to the nth power. Your second term in the binomial is going to start to the 0th term, or the 0th power. And A is going to decrease as you go on until you get to the 0th power. B is going to increase from 0 until you get to the nth power, in the same way that your expanded 1b increased in that way. Okay? Now, when it comes to evaluating these little coefficients, you can always resort to combinations. There is one little shortcut method. If you can generate Pascal's triangle at any time, Pascal's triangle will calculate the coefficients, if you remember ever having done anything with Pascal's triangle. I'm not exactly sure why it paused there, but this animation should continue. I won't touch anything until it does. Basically what happens is numbers get added together to form new things, like that. So basically 1, you start with a 1. This is the 0th power, or the 0th row. This is the first row. This is the second row. This is the third row, and this is the 4th row. The second number in the row determines the row number. But what you'll notice, this should look familiar, 1, 3, 3, 1. This is another way of calculating coefficients or the combinations. So for instance, right here, these numbers 1, 3, 3, 1 can be calculated by doing 3C0, 3C1, 3C2, and 3C3. So Pascal's triangle is a quick and slick method of coming up with binomial coefficients. In the next video, you will actually see this using the formula to expand the binomial using both the combination method and the Pascal method.